welcome back. So, let us continue from where we left off. We were talking about the linear combinations of two efficient portfolios being efficient. And as I mentioned, if I take two portfolios P and Q and solve the optimization equations and they would be satisfying the optimized equations because they are efficient portfolios. Now, if I take a linear combination of P and Q, I find that the new portfolio, that is alpha P plus beta Q, will also satisfy the optimization equations with a different risk free rate. So, the outcome is that if we form linear combinations of efficient portfolios, we get another efficient portfolio. So, how does this help us? It helps us in the sense that the entire efficient frontier can now be defined as the locus of linear combinations of two efficient portfolios. I repeat, the entire efficient frontier is now the locus of linear combinations of two efficient portfolios. Hence, if we know the coordinates of any 2 points on the efficient frontier, that is say P and Q, we can trace the entire efficient frontier, because every other point will be a linear combination of these 2 points. I repeat again, if we know the coordinates of any 2 points on the efficient frontier, say P and Q, we can trace the entire efficient frontier, because every point will be a linear combination of these 2 points. Thus, the problem of tracing the efficient frontier turns out to be a 2 security problem. It resolves down to 2 security problem, because see, we are all having 2 portfolios P and Q which are efficient, and we want to work out combinations of these 2 portfolios. Now, portfolios and securities, in so far as portfolio management is concerned, are identical in the sense that they represent points in risk return space. So, whether we are talking about portfolios or we are talking about securities, it tantamounts to the same thing in so far as the risk return space is concerned. So, they represent points in the risk return space, whether it is a single isolated security or whether it is a combination of securities representing a portfolio. So, the bottom line is that we want to work out linear combinations of 2 securities P and Q, which may be portfolios, but we take them as securities because it does not really matter. They are identified by a pair of numbers in risk return space. So, that being the case, we have P and Q. If we are able to identify them in risk return space, and then we form linear combinations of P and Q, just as we form linear combinations of 2 securities A and B, and then we arrived at the hyperbola that contained all the portfolio possibilities curve, and then out of that we identified the efficient frontier. So, the same process, the same exercise can now hold for these portfolios P and Q, but the result that we are going to get now is the set of efficient portfolios comprising of the n securities that we started with. So, we have now resolved this n security problem to a 2 security problem. We identify 2 efficient portfolios and we take linear combinations of these 2 efficient portfolios in the same manner as we had linear combination of 2 securities A and B, and using the same process, same methodology, parallel absolutely, we end up with the efficient frontier of P and Q, which is essentially the efficient frontier of the n securities A, B, C, D, N up to n. So, I repeat, let me repeat, it is worth repeating. We have got 2 efficient portfolios comprising of the n securities A, B, C up to n, and P portfolio corresponding to the risk free rate of 5% and Q portfolio corresponding to the risk free rate of 2%. We have these 2 portfolios which are efficient. Let us forget the name portfolio, let us call them securities. So, we have got 2 securities P and Q, and we know that our efficient frontier that we are desperately looking for is a linear combination of P and Q, and we also know that given any 2 securities A and B, how to form linear combinations, and the outcome is the hyperbola, and the arc of the hyperbola forms the efficient frontier beyond the point of minimum variance. So, in other words, that methodology completely devolves down to the current problem in terms of the portfolio of securities P and Q, and the efficient frontier comprising of P and Q is also the efficient frontier comprising of the securities A, B, C up to N, and therefore, the problem that we started with of N securities has now been resolved to a 2 security problem. So, let us continue. So, we continue with our 3 security problem to illustrate this method. For RF P equal to 5%, we had the portfolio P as the point of contact of the tangent from F to the arc of the hyperbola in the plane Z is equal to 1 by 6, and we had this composition x P1 is equal to 14 by 18, x P2 is equal to 1 by 18, x P3 is equal to 1 by 6. Sigma P is equal to under root 203 by 6 and R P is equal to 44 by 3. This was the situation for the portfolio P, where F P was tangent and which corresponding to F equal to or RF equal to 5%. Then we did the same exercise with RF equal to 2%. We found a new optimal hyperbola, we found a new plane which was given by Z is equal to 1 by 20, and the essentials or the cardinals of this new point Q, which lies on the hyperbola and which is the tangent where F no F is the 2% one. So, F Q is the tangent to this new hyperbola which lies on the plane Z is equal to 1 by 20, where F corresponds to a risk free rate of 2%, and the composition of this point Q is x Q1 is equal to 7 by 20, x Q2 is equal to 12 by 20, x Q3 is equal to 1 by 20, and when we work out the cardinals, the standard deviation and the expected return of Q, we find that sigma Q is equal to under root 5481 divided by 400, and sigma R Q is equal to 107 upon 10. So, again we have full information about both the portfolios P corresponding to the risk free rate of 5% and the portfolio Q corresponding to the risk free rate of 2%, and reiterate that both P and Q are efficient because they have been obtained by solving the fundamental optimization equations. So, they naturally have to be efficient. Now, we know we form a linear combination of P and Q. As I discussed just now, we form a linear combination of P and Q. For simplicity, for minimization of calculations, we form the simplest possible linear combination, that is half of P and half of Q. We mix half of P and half of Q in terms of the amounts, of course. The coordinates of W, this new portfolio we call W. In other words, we constitute a portfolio W which comprises of 50% of Q and 50% of P. So, combining these two, 50% of P, 50% of Q, we form a new portfolio W. The cardinals of the portfolio W can be easily derived because it is a weighted portfolio of P and Q. So, we have x W1 is equal to 203 divided by 360, x W2 is equal to 118 divided by 360, and x W3 is equal to 39 divided by 360, and sigma W is equal to under root 21.859. In other words, sigma W square, the variance of W is equal to 21.859, and the expected return of W is equal to 4566 divided by 360. Now, it can be shown, if you use this process, if you use the reverse process of the optimization equations, it can be shown that W is efficient, it will solve the optimization equations, but with a risk free rate of 4.068966%. So, I repeat, this portfolio W that we have formed of half of P and half of Q can be explicitly shown to satisfy the fundamental optimization equations, and hence it is an efficient portfolio comprising corresponding to a risk free rate of 4.068966%. But because W now is a very important point, this is a very important slide. Now, W is equal to 0.5 into P and Q. we know the cardinals of P and we know the cardinals of Q. In essence, we know the variance and the covariance and the expected return of P and Q and the variance and expected return of Q. For the moment, let us focus on the variance. We know the variance of P, we know the variance of Q. We know the weight of P, we know the weight of Q. What do we know? What do we not know? What we do not know is the covariance between P and Q. So, if we can find out the covariance of P and Q, we are done. Our problem is solved. We have a 2 security portfolio where all the parameters are given. We have the expected return of P and Q. We have the variance of P and Q. And if we can find out the covariance between P and Q, we can simply plot the portfolio possibilities curve, the hyperbola, and the efficient frontier can be identified therefrom. So, for our problem boils down to finding the covariance of P and Q. To find the covariance of P and Q, we use a ingenious trick. We know that W comprises of 50% of P and 50% of Q. Therefore, the variance of W will consist of, which is already given, which we have already derived. From where have we derived? We have derived it from the composition vector of W. Using the composition vector x1W, xW1, xW2, xW3 and the variance covariance matrix of A, B and C, we are able to derive the covariance of W and we find it to be 21.859. We have already done that exercise in the previous slide. But W consists of half of P and half of Q. Therefore, the variance of W, which we have derived as 21.859, must be also equal to what? 1 by 2 square sigma P square plus 1 by 2 square sigma Q square plus 2 into covariance of P and Q into 1 by 2 into 1 by 2. This is the standard formula for the variance of a 2 security portfolio. Now, we are using where P and Q are the 2 securities. As I mentioned, it does not matter if we are having a security or a collection of securities called a portfolio. It is simply a nomenclature. So, we now have sigma W square, which is already derived as 21.859 as given by this expression. We also know sigma P square. What is sigma P square? Sigma P square is 203 upon 6. And what is sigma Q square? Let me check. Sigma Q square is equal to 5481 upon 400. I repeat, sigma P square is equal to 203 upon 6. Sigma Q square is equal to 5481 upon 400. So, we know sigma P square, we know sigma Q square, we know x q, we know x p. So, what else is left? The only thing that is left is the only unknown in this equation is sigma p q, the covariance between P and Q. If we solve this equation for sigma p q, we end up with getting sigma p q is equal to 19.95. I repeat, sigma p q is 19.95. Now, as far as portfolio P and Q are concerned, what information do we have? We have sigma P, we have sigma Q, we have sigma P Q, we have expected return P, we have expected return Q. All the cardinals that are required for working out the efficient frontier or the portfolio possibilities curve of this pair of risky securities P and Q is available with us. We simply do that exercise as we did in the 2 security risky problem to obtain that hyperbola and the arc of the hyperbola representing the efficient frontier, and we do that exercise. When we do that exercise, what we get is x square is equal to 0.4853 y square minus 7.2353 y plus 35.5588. So, what I have done, let me reiterate. I have simply used these parameters the information about the variance covariances of P and Q and their expected returns. I have used the feasibility equations and eliminated x p and x q from them, and the result is the hyperbola that we did in the 2 security risky problem, which is represented by this equation. X square is equal to 0.4853 minus 0.4853 y square, I am sorry, minus 7.2353 y plus 35.5588. This is the hyperbola that represents all feasible combinations, that is the portfolio possibilities curve comprising of P and Q. And please note, these P and Q are themselves combinations of securities A, B, C up to N and in various proportions. We have got now is the portfolio possibilities curve comprising of P and Q. The equation for that we have already got, is the equation and that is represented here. Now, now suppose we want to work out that a portfolio with a risk tolerance of say given as 16% without any risk free lending and borrowing. What do? We plug in x equal to sigma t, where t is the name of the portfolio that we are arriving at, x t equal to 16% in this expression in this portfolio possibilities curve. X square is equal to 0.4853 y square minus 7.2353 y plus 35.5588. We get y is equal to r t is equal to 30.035%. And now we can solve the expression for the expected return in terms of the composition vector. We get r t is equal to x t p r p plus 1 minus x t p r q. We know r p, we know r q and we know r t as well. We can find out the content of x t p, that is the composition of p in t, and the full composition of t in terms of A, B and C is now obtained as x t I is equal to 4.87 x p I minus 3.87 x q I, where I represents A, B and C. So, now let me recap what we have done. I have spoken in a bit of haste. So, let us go back and let us recap what we have done after arriving at the portfolios P and Q. Now, we know sigma p, sigma q, r p, r q and sigma p q. That is all that is required for determining the portfolio possibilities curve comprising of p and q. And we can trace out the curve between the standard deviation and expected return for any arbitrary combination S of P and Q as in the two security problem. So, that gives us the portfolio possibilities curve from which we can identify the efficient frontier. Now, construction of the efficient portfolio. If we want to construct a portfolio, efficient portfolio corresponding to a given parameter. Let us say we want to construct a portfolio T corresponding to a given level of risk. We simply plug in the value of sigma t in the portfolio possibilities curve and that we have obtained, and we arrive at the corresponding value of r t. I repeat, we have got the equation of the hyperbola which is a combination of P and Q, a linear combination of P and Q. For choosing an efficient portfolio or for working out an efficient portfolio corresponding to a given level of risk, what we do is, let us say sigma t is the given level of risk corresponding to a portfolio T which we want to determine the composition of in terms of A and B, A, B and C. We are given the composition of we are given the risk of sigma t. We solve this portfolio possibilities curve equation and we given sigma t we can find out r t. Now, we have r t is equal to x t p r p plus 1 minus x t p r q. So, this is the second step. Now, in this equation, if you look at it carefully, we know r t, we have found out r t. How? We have found out r t by substituting sigma t, which is a given parameter by the investor, and substituting in the portfolio possibilities curve, we get r t. Using that r t, we know r p and r q as well, they are already derived. Let me repeat, r p is equal to 44 by 3, r q is equal to 107 by 10. So, we know everything in this equation except x t p. So, from this equation we can find out x t p. If we know x t p, we can find out x t q. So, we know the composition of p and q in t, but we also know the composition of ABC in P and ABC in Q. So, we can find out the composition of ABC in T. So, that is the stepwise methodology that we follow. If we are given a level of risk tolerance, then we can determine the efficient frontier comprising of n securities given to us. Then I discussed this example. If Rp is equal to 5%, we have this result. If Rp is equal to 2%, we have this result. Both of the results we have already derived, and which are here in this which are summarized here once more. Xp1 is equal to 14 by 18, Xp2 is equal to 1 by 18, Xp3 is equal to 1 by 6. Sigma p square is equal to 203 by 6, Rp is equal to 44 by 3. For Rf is equal to 2%, we get Xq1 is equal to 7 by 20, Xq2 is equal to 12 by 20, Xq3 is equal to 1 by 20. Sigma q square is equal to 5481 upon 400, Rq is equal to 107 by 10. We have also found out that sigma pq is equal to 19.95. We can get the equation of this hyperbola as x square is equal to 0.4853 y square minus 7.2353 y plus 35.5588. This is the equation of the hyperbola as it should be, because it is the portfolio possibilities curve of a two security portfolio P and Q. Now, let us take this example. Let us carry forward this example. Suppose we want to construct a portfolio T having a risk tolerance of 16%. We plug in sigma T equal to 16% is equal to x, and we find the value of y, which represents the expected return of T. That comes to 30.035%. Using this return of T, which is now obtained as 30.035, we can find out the content of P in T, and then we can find out the content of Q in T. Using the content of P in T, the content of Q in T, we can find the composition or the content of A, B and C in T. So, this is how the portfolio optimization problem in the mean variance portfolio optimization can be solved for n securities. The procedure can be directly extended to n securities, where instead of 1 to 3 we can have 1 2 3 4 up to n. So, the 3 security problem completely epitomizes, completely captures the features of the n security problem. So, let us continue. Let us start with some examples. Two securities A and B have coordinates A 6 by 12 and B 8 by 8 comma 20. Let me repeat, two securities A and B have the coordinates A 6 comma 12 and B 8 comma 20 in risk return, that is sigma expected return space. The correlation coefficient between the returns is -1. Calculate the return in percentage on the risk free portfolio comprising of A and B. The solution is quite simple. We know that if the two securities are perfectly anti-correlated, then the risk free return is given by sigma 1 R2 plus sigma 2 R1 divided by sigma 1 plus sigma 2. You have got the values of all the contents or the constituents of this formula. You have got sigma 1, you have got sigma 2, you have got R1, you have got R2. Simply plug in the values, you get the expression for the risk free rate, which is 15.4285%. Alternatively, you can go through a slightly longer way. You can find out the content of A in the risk free portfolio, that is given by sigma B divided by sigma B plus sigma A. The content of B would be 1 minus x A. You know the content of A and B, you know the returns on A and B. You can work out the risk free rate. So, either way you arrive at the answer of 54.4285%. Let us look at a slightly more interesting example. Two securities A and B have coordinates 8, 12 and 12, 24 in sigma expected return space. The correlation coefficient is 0.50. An efficient portfolio P is to be constituted using long oblique short positions in these two securities without risk free borrowing or lending, with a desired expected return of 80%. please don't get disturbed by this 80%. I have put in this figure specially to highlight certain things, as an exorbitant rate of return, but this highlights, this conveys a message which I shall tell you. Calculate the standard deviation of this portfolio in percentage. Well, what are we given? We are given sigma A R A or sigma 1 R 1, we are given sigma 2 R 2, and we are given rho 1 2 or rho A B as the case may be, and we are also given the expected return on the target portfolio, that is given as 80%. So, using the first equation that we have on the slide, R P is equal to, or the expected return on the portfolio is the weighted average of the expected return of its constituents. I can work out the composition or the content of the target portfolio, which requires the expected return of 80, and we find that X A is equal to minus 4.67 and X B is equal to 5.67. Now, it is very simple to find out the variance. Why? Because we know X A, we know X B, we know sigma A, we know sigma B, we are also given rho A B, and remember the covariance A B is equal to rho A B sigma A sigma B. So, we know everything in this formula, and we simply have to plug in the values, and what we get is the variance is equal to 3479.11 percentage squared, and therefore, the standard deviation is 58.98%. Another problem, two securities A and B have coordinates 8, 12 and 12, 24 in sigma expected return space with rho A B equal to 0.50. An efficient portfolio, please note this word efficient, it is very important. An efficient portfolio is to be constituted using long oblique short positions in these two securities together with risk free lending or borrowing. So, we have freedom as far as long short positions in the securities as well as risk free lending and borrowing with an expected return of 80%. Calculate the standard deviation of this portfolio. Please note again the expected return is 80%, and as far as the other parameters of A and B are concerned, they are similar to what we had in the immediately preceding example. Rho A B is equal to 1 by 2 and the coordinates of A and B are 8, 12 and 12, 24 respectively. So, the first step is to calculate the equation of the portfolio possibilities curve, which we can do in the standard procedure using the feasibility conditions, and we arrive at the portfolio possibilities curve, which is given by 144 x square minus 112 y square plus 3072 y minus 29952 is equal to 0, equation number 1 on the slide. I repeat, this is simply obtained by eliminating x 1 and x 2 from the expressions for the expected return and the variance of the portfolio, which is targeted as to have a return of 80%. So, assuming that the targeted portfolio has the standard deviation x and has the expected return y, and we solve the we solve the feasibility conditions, eliminate x 1 and x 2 from them, and what we get is this equation of the tangent. Now, the tangent, now we are given that the risk free rate is 9%. Therefore, the efficient frontier is the straight line joining the point F, which has the coordinate 0, 9 with the arc of the hyperbola, which is represented by equation number 1. So, to obtain the equation of this tangent, which will be the efficient frontier, what we do is we assume that y is equal to mx plus 9 because the y intercept is 9. So, we assume that y is equal to mx plus 9 is tangent to this particular hyperbola. Let us say this is equation number 2. Now, substituting equation number 2 in equation number 1, what we get is the equation right at the bottom of your slide. Now, because we want that equation number 2 should be tangent to equation number 1, it is necessary that the roots of this equation must be the discriminant of this equation must be 0, the roots must coincide, the discriminant must be 0, and when we solve for the discriminant of this equation equal to 0, we can get the value of m. The value of m turns out to be 1.283. Please note, we are neglecting the other value of m because that would give us the other tangent to the hyperbolic arc, which is redundant for our purposes, because we are considering or we are concerned with the efficient frontier only. Hence, we are concerned with the upper tangent, the tangent with the positive slope, and the upper tangent which lies on the upper side of the two tangents, because that would be the efficient frontier. So, we have m is equal to 1.283, and hence we know the equation of the tangent. The equation of the tangent is given by y is equal to 1.283 x plus 9. Now, we are given that the standard deviation, the expected return of the target portfolio is 80. So, substituting y is equal to 80 in this equation, we get the value of x, which is 55.34. So, this is the solution of this problem. The interesting point that you would observe in examples 2 and 3 is that while the expected return in both cases is 80, the standard deviation in the case where short sales, where riskless lending or borrowing is not allowed, was slightly higher. It was slightly above 58%. However, when you allow risk free lending and borrowing, you can construct a relatively better portfolio, a relatively superior portfolio, a portfolio which is even more efficient because it has a lower standard deviation corresponding to the same level of expected return. So, in other words, what I simply want to convey by this pair of examples is that if you add risk free lending and borrowing to your feasibility structure, you are able to enhance value of your portfolio optimization problem in the sense that you can construct a portfolio which is better than the portfolio, which is superior to the portfolio that you would have constructed if risk free lending and borrowing is not allowed. I shall continue from here in the next class with the single index model. Thank you.